So for this video, we're going to take our descriptive statistics and we're going to describe data using histograms and polygons. But we're going to actually get into a very specific kind of histogram and a very specific kind of polygon graph. And these are the relative histogram and the relative frequency polygon. So this is going to mean we're going to need a calculator, because we're going to be converting these actual whole number units into percentages. Okay, so first thing we need to do is we need to look at our data, because we're just given raw data here, and where this data has come from. It's come from somewhere that looked at 40 different types of fast food and measured how many grams of protein are in each of these 40 different types of fast food. So we probably have some burgers, some chicken, some cheesy kind of fast food item, and we just want to see the distribution. If we just had these 40 pieces of data, you can just see that there's really no clear answer to what is the distribution. So we're going to start to organize this in a table, and I would suggest by starting off with finding the maximum value and the minimum value. Well, the maximum value, if you look carefully in the fourth row, is 57. And the minimum value, the one value that has the least amount of protein, is in the third row, and that's 12. Then we need the range. We need to take our maximum minus our minimum and subtract the two. So 57 minus 12, and 57 minus 12 is equal to 45. Okay, so now that we have our range, we can start to do something very useful to create these limits and boundaries. We're going to look at the number of classes. A class is another way of saying a group. We're going to break all of this data into 6 groups of equal size. And there's not going to be the same amount in each size. It's not like we're saying, the same amount will go in each. We're just going to take from the lowest to the highest values and break that into 6 groups. And to do so, we will take to find our class width. Oops, hold on. Holding on to the wrong thing. Class width will be taking the range and divide it by the number of classes. Now there are 2 ways to find the number of classes in the problem. One way is to just see which one, just straight out what they tell you to do. And the other way is to look at the number of a number of rows. And the number of rows will tell you how many classes there are. Okay, so in doing so now, what we are going to do is we are going to start with our lower class limit. And that is going to be the minimum. To find the class width, we take our range, which is 45, and divide it by the number of classes, in this case 6. 45 divided by 6 is equal to 7.5, or 7.5, which I am going to round up to 8. Now, the main reason for rounding up is because if I rounded down, that would first of all be incorrect with the 7.5, but more importantly, if I didn't round up, then I may not have been able to get to 57 if I rounded down for 6 different rows. So 12 is going to be my start, and my class width is 8. So what I would do is take that 12 and add 8 to it to get to this number, 20. Now, you'll see that I'm writing very far to the left because I'm actually going to put a lot of information inside of this space right here. But I want to show you that this space goes from 12 to 19. See, I'm only using about half the room. I'll show you why in a moment. 12 to 19 tells me that there are 8 spaces in this class. If we count from 12 and go 12, 13, 14, 15, 16, 17, 18, 19, that's 8 inside of that class. Now, if I keep going up by 8s, so 28, 36, 44, and 52, now I have the lower limits of all of my classes. And now we're going to go to the upper limits, or the higher limits. So this is going to be 27, this is going to be 35, this is going to be 43, this is going to be 51, and this is going to be 59. Okay, so with that in mind, I now have all of my lower limits, and now I can go to my higher limits up here. You'll notice that there is no overlap between the higher limit and the next lower limit. And if that was the case, then I might have a data point that's in 2 different classes. And these classes have to be, now check this vocabulary word, mutually exclusive. The classes have to be mutually exclusive, so no fast food data can belong to one and the other. Now this is what is most common in most statistic books, are the idea of limits. Although sometimes you get into boundaries, which means they take this limit and they drop it by a half step. And then they take this limit and they make it go up by a half step. So it's going down 0.5 and up 0.5. And this now becomes a boundary. Now you can choose one or the other, and I literally think you're going to be more successful choosing the limits. But again, I've seen books go from 11.5 to 19.5, and then you would do the same with 20 to 27. Go down a half step to 19.5, and go up a half step to 27.5. Now you'll notice that there is overlap between the higher boundary and the lower boundary of 2 adjacent groups or classes. But you don't need to worry since there are no half-step data points. The boundaries go into a level of a decimal that is actually not part of our data set. And so we'll continue with 27.5 to 35.5 and 35.5 to 43.5 and 43.5 to 51.5, and then finally 51.5 to 59.5. So you're doing these notes that will be turned in at the end of each unit, and this note set should have both of these written down, although I do expect that on the homework you would just do the limits, or whatever's easiest. So now I give you this column called tally. And this is really nice because it allows you to make tally marks as you count up the data pieces. So taking a look at this set of data, we're going to check to see how many data pieces are between 12 and 19, including 12 and including 19. I'll switch to a highlighter here, and I'll look through the first row, and as I scan along that first row, I'm not seeing anything that's as low as 12 and as high as 19. If I go along the second row, 15 does fit between 12 and 19, and so does 18 and 19 and 12. There's our minimum and maximum inside of this class. And then 15. So if I was doing this with my finger instead of a highlighter, I would go, okay, 1, 2, 3, 4, 5. And I make 5 tally marks. And as I get done with the 5th tally mark, I draw a strike through it, and that allows me to count very easily at the very end. So let me finish with my highlighter. I'm moving along the 3rd row and see 14 and 12 again, and then I move along the 4th row and see nothing else. So again, if I was using my finger, I would have 7 tally marks for a total frequency of 7. There are 7 data points, or fast food items, between 12 to 19 grams of protein. Now, I could have you do this for the next 5 minutes, but instead, how about I put down the tally marks, like so, and then you can write the frequency. Or I will write the frequency and you write the tally marks. All right, we can kind of like have fun with this a little bit by changing this up. All right, you can pause the video here and try to figure these missing gaps out yourself, kind of modeling some of the homework you might be doing. If you've unpaused the video, if you've done this part, you can see that this has 3 sets of 5 and a 2, which makes 15, plus 2 is 17. A 10 would be 2 sets of 5, and this would be 4, and this is 1 tally mark, which means a frequency of 1 for both the last 2 classes. So this is my frequency f. Relative frequency is taking my f and dividing that by the sample size n. I said a few times, but it might have blown past pretty quickly, that there were 40 pieces of fast food. Now, a couple ways to find this out. You could count up all these numbers, or you could see that there are 4 rows of 10, which would give you 40. Finally, another way to do it is to just add up all of these frequencies, and the total of f is equal to n, which is equal to 40. So I'm now going to take my f and divide it by n. So I'm going to go 7 divided by 40. And 7 divided by 40 gives me a 3-digit decimal of 0.175 or 175 thousandths. Now what's great about this 3-digit decimal, it's in the perfect form to convert to a percentage. This is 17.5%. The next one's going to be 17 out of 40, which also makes a 3-digit decimal, 0.425 or 425 thousandths, which says that 42.5% of our fast food has between 20 to 27 grams of protein. So that would probably be your most likely outcome, is to get, so if you're looking to get over 20 grams of protein, then most likely you're going to pick, one that lands in that category, or more, to be honest. Something very interesting is going to happen when we have this frequency of 10. If we go 10 divided by 40, then we get an answer of 0.25, or 25 hundredths. Now, I think it would be best to put a 0 here, because the 0 is going to be the easiest way to compare it versus the others. And this is incredibly important as we do our data moving forward, because we're going to want to compare them and we're going to want to draw this histogram accurately. So let's make sure that we have 3 digits on our decimals. And I know this flies in the face of your middle school mathematics teachers who say never put zeros in after the decimals because they're not needed. Well, this is when they're needed for comparison purposes. So 4 divided by 40 gives you 0.1, but that's really 1/10 or 100 thousandths, and 1/40th twice gives us 25 thousandths, but that's 0.025. Notice that the 0.250 and the 0.025 are vastly different things. So for our final column, we're going to do cumulative frequency and cumulative relative frequency. It's easy to get these two confused, because cumulative frequency is just when you take your frequencies and sum them up. So this is the sum of f. So 7 plus 17 is 24. 24 plus 10 is 34. So that's basically saying that 34 data pieces are less than or equal to 35 grams of protein, because it includes the previous 2 classes. And then we have 38, add 1 more, 39, add 1 more, 40. So the cumulative frequency is the sum of f. The cumulative relative frequency is to take the sum of f and divide it by n. So this is going to be 7 divided by 40, which is 0.175. This is going to be 17 divided by 40, which is, sorry, not 17. Sorry, let me change that. This is going to be 24 divided by 40, and 24 divided by 40 is 0.6, or 600 thousandths. This is going to be 34 divided by 40, and 34 divided by 40 is 850 thousandths. Now, you can decide to keep writing these fractions out if you'd like to. 38 divided by 40, or just typing it in, is 950 thousandths. And then 39 divided by 40 is 975 thousandths, and then 40 divided by 40 is 1. But I'm stylistically putting that 0.000 after it so you can compare it versus the others. Okay, so now what we're going to do is carefully create our relative frequency histogram. And I'm going to need to see, for this, the relative frequency chart and my limits. So, to highlight these in green, I'm going to look at this, and I'm going to look at this for my heights and my widths. This is going to be my x-axis, this is going to be my y-axis. For the problem down below, we will use the same relative frequency for the y-axis, but we will not be using the same exact scale. I mean, we will be going by eighths, but we won't be using the same exact x values, because the relative frequency histogram should start at the minimum and then go up by the lower limit of each class. So this goes up by 8, this goes up by 8, this goes up by 8, so on and so forth. Now, you might notice that sometimes the book and sometimes the online homework, instead of starting with the minimum, they start at the easiest value, let's say 10. Or if this was maybe the minimum was like 19, they would start at 15 if they were going up by 10, starting with, every, because you can't start at 20 if your minimum is 19. So they just started at an easy number. So 10 sometimes ends up as being one of those answers. I like starting it at the minimum, because then you're sure not to overshoot your maximum. So here we start with the minimum, and it goes up by 8 each time. And so here I have my limits. You'll notice now what we need is a y-axis. Now, I know that there are probably some previous statistics instructors who may have said, oh, just make it easy for yourself, just go from 0 to 100%. That's pretty misleading, especially because you'll notice that our highest relative frequency is 42.5%, or 425 thousandths. If we went to 100%, or 1,000, then our graph would look squished, or squashed. And that's going to be bad because that's actually lying with your statistics. You're actually being deceptive. If you're making it so that your y-axis makes your data look squashed, that really changes the perception of the problem itself. There's a lot of perception making in descriptive statistics. So I want to warn you against that. So I honestly have a criteria that you should look at the highest relative frequency, and that's 425 thousandths. So it looks like we should have 425 thousandths near the top here, but it really is going to take us some time to think about this. So maybe instead of going all the way up to 425, where the 425 is the last number here, I don't like that just from the idea that I don't have an easy way to count to it. So let's drop the decimals just for a moment and consider these as whole numbers. If I had to get from 0 to 425, would I want to move by ones? Well, absolutely not. That'd be 425 tick marks. Would I want to move by 10s or 25s? Nah, it'll still take me a long time to get there. Well, maybe moving by 50s would be easy. So the first tick mark would be 50, and the second tick mark would be 100. And the third tick mark would be 150, and this would be 200. Skip, 300. Skip a tick, 400. Whoops, that happened again. 400. Skip a tick mark, 500. All right, sometimes when I put too many marks on the screen, it gets a little clustery. So now what I'm going to do is I'm going to put back all of my decimals, and you can see that this is now a proper y-scale for my relative frequency histogram. And it's not just a histogram. A histogram would just be putting 17 bars in the first column and then, or 7 bars in the first column and 17 total here and 10 total here, and that's all fine and good. But it's important to know the relative frequency histogram because we need to see these wonderful percentages. So let me get some heights onto this now. And I'm doing that because this first graph is 17.5% of the data, or 17.5% of the data, which is 175 thousandths. This second bar is 425 thousandths. This third bar is 250 thousandths, which is halfway between the 200 and 300. And this graph is 100 thousandths. And our final two is 25 thousandths here and 25 thousandths here. And, well, we went off, but actually we went off our scale a little bit, but this just means we got to fill this in. This bar, because we had this data set, there was one fast food item between 52 and 59, then this here should be written. And I used a 60 because I went up with a space of 8. Now over here on the left-hand side, we should label what we're talking about. So this is the relative frequency. Oh, don't do it again. Relative frequency. Got a little bit of stuff there. And then over here, this is going to be our x-axis, which is going to be our protein in grams in fast food. Oh, come on, don't do this to me. All right, cool. Protein of grams in fast food. Now, I do want to put maybe just one little note on the process here, is that you don't have to use 12 through 20. You could have went, in the first section, 11.5 to 19.5. And then right next to it, you would have 19.5 to 27.5. So you see how my x-axis could be that way? But it just gets so sloppy. It gets just like the numbers are right on top of each other. It's harder to write. And here, this tells the story that between 20 and 28, you had roughly 42%, 42.5%. Even if you couldn't read it so well, you could see that this bar here is over 42%. Or over 40% of your possibilities here. And now we'll do the relative frequency polygon. So for this final example here, look at how we can do this relative frequency polygon, which the side here will be relative frequency. And along the bottom here, we are going to have our medians of protein in grams. So what's important about this process is the x-axis is in medians. And to find a median, you take your low number, add your high number, and divide it by 2. So one way you could do this is you can take the 12 plus the 20 and divide that by 2, and this would give you 16. Another way you could have done it if you use decimals up above, 11.5 plus 19.5 divided by 2, and that would give you 15.5. Now, you can do that for the next set, which is 20 plus 28 divided by 2, and that gives you 24. But another nice thing is looking between these two, you can see the gap is 8. And the gap is the same distance that is inside of all of our classes. So 24 plus 8 would give you 32. And then if you went 36 plus 44 divided by 2, you'd get to 40. Then 48, 56, and you'll see we'll need to go one more. But let's now figure out our y-axis. Well, what's lucky about the y-axis is that the y-axis is exactly as it was up above. We're going to take it to 50%, or 0.500 at the top tick mark, and then every 2 tick marks we'll go down by 100 thousandths until we get to 0. So, using what we have at the top there, we see that our first class has 175 thousandths, or 17.5%, and so that gets us our first dot. Now, we're not going to connect the dots just yet. Let's just plot our dots. And the second dot is up to 425, or 0.425. The next one is going to be 0.250, which is halfway between 200 and 300. And the next one's going to be 0.100, or 100 thousandths. And the last two are going to be 25 thousandths. Now, what's important about this is I want to definitely make sure you connect the dots correctly. You not only connect the dots between the points you've plotted, but you also have to connect the dots to the ground to make this frequency polygon. Now, it's important to know why we do this. Well, first of all, a polygon is a many-sided object. Like a square is a four-sided polygon where all angles and all sides are equal. A rectangle is a polygon, four-sided, with different properties, 4 right angles. Pentagon is a polygon, and this is a polygon, but we don't want to leave. You'll notice that this is not connected. We need to connect this to the next tick mark, and then we would need to go back and make sure this is marked, and this gives you this answer here. Oops. I want to make sure I get the color here. Come on, give me the right color. 60. So now I can see that 425 thousandths, or 42.5% of the data, has roughly 24 grams of protein. But I can also, like the histogram you made above it, see the shape of the data. And this shape of the data seems to be skewing to the right, and we're going to formalize our language about symmetry and skewness in a later unit. But what's cool about the frequency polygon and the frequency histogram is you see skewness and symmetry. You see the shape of the data. And that's the key to descriptive statistics. Descriptive statistics is showing you the data in a very descriptive way, pictorially. So this is the end of this problem, and you did a great job getting to this point. Again, the big notes on the process is your x and y axis are somewhat standardized, though the x-axis can use the boundaries that you set up in your table, or you could use whole numbers if you can keep track of that. Like I did, I felt it was pretty easy to do that. The relative frequency polygon uses medians, not the ends or the edges of each boundary, so that's something you'll have to calculate. Well, thank you very much for meeting me at the end of this video. I appreciate your hard work, and we're going to have a short video next covering time series graphs.